So welcome everybody to the monthly meeting for Tucson Amateur Astronomy's Fundamentals Group. I don't have the participant list yet. On a second. The couple names I don't recognize, couple returners. So, for those who haven't attended this meeting before, this meeting is typically divided into two parts where we talk about either a constellation or an amateur, a professional astronomer of note that did something that we as amateurs would find useful in our to know in our day-to-day observing or just background knowledge, or we do detail a constellation. Generally want to try to get one that's at least in the sky at or near the time of the meeting. So this month I'll be talking about the Constellation Hydra, fit that void. And then after that presentation, we normally have a main topic, which can be covered a wide variety of things. This month, I will be talking about a lot of the units and measures that professional astronomers use in their research that will, for those who occasionally find themselves winding down a Wikipedia rabbit hole and looking at like, what does all this stuff mean in that right-hand bar? Hopefully this will help answer some of those questions, but also give you a better way to ground some of the numbers to something that you can actually relate to rather than just being like, hey, that's a number. I don't know how big it is or where it all fits in the grand scheme of things. So hopefully just building out some of that knowledge, which is useful if you like you read or follow things online in astronomy, both amateur and professional. So when I get everything. So starting off with Hydra, it is by area the largest constellation in the night sky. Uh, Typically, it feels that weird thing of being a very long but somewhat thin constellation. But despite this, it's visible for about 1/4 of the total sky. It covers approximately 6 hours of right ascension. It has the designation of being one of the original 48 Greek constellations that was cataloged by Ptolemy in the second century. Um, but it does, like many of the constellations that, especially the zodiac constellations, they were known also to the Mesopotamians, Babylonians specifically, but underneath different names. To be sure, although there are a lot of similarities between the tales that the Greeks came up with, well, borrowed for some of their constellations. Despite being visible for covering 1/4 of the night sky, it is best visible from about February to late early February all the way through June before it starts getting into positions where it's setting, where it has set completely. Within it, despite having the distinction of being off the galactic plane, there aren't really any bright nebulas in this area, or even any dark nebulas. A slew of galaxies. Uh, mm, that should be. That seems to be a typo for me, left over from a previous constellation in terms of two notable nebulae. But there are a slew of galaxies that are brighter than magnitude 12, which I typically limit myself to when reporting these, because once you get darker than magnitude 12, you really need some decent optics, decently sized aperture optics in order to make the most out of those objects. They start getting pretty small pretty quick for galaxies. And you also would need really good skies for some of them. Of the objects that we would find of interest are two Messier object, three Messier objects. Excuse me, that's a typo. One of them is an open cluster, M48. One of them is a globular cluster, 68, and then a spiral galaxy M83, which will show images and statistics for those three here at the end. Of the 30 galaxies that I mentioned that are brighter than magnitude 12, the majority of those are smaller than 10 arc minutes, which does make them objects you would reasonably need high magnification to see, that you would typically be associated with optics somewhere in the range of 10 and 8 inches or more. That also contains two galaxy clusters in the Able catalog that are ready up here, but I will not talk about those because the Able catalog is somewhat challenging to observe. Some other things is that the constellation is actually the origin point, or what's known as the radiant, for two different meteor showers. Although these are relatively minor meteor showers that would be difficult to distinguish between the normal background fall rate unless you knew when they were. Unlike the Perseids, where you can, or the Geminid meteor showers, which are some of the more active, two of the most active meteor showers that occur throughout the year. So these are mostly from passerby comets, and their material has been fully depleted or fallen into the earth. So the reason why they have such low fall rates. But they're also in early December and late January. So it's generally cold outside. So it's generally not worth it to go see these meteor showers unless you're, in the southern hemisphere where it's actually summer. Of the stars in the constellation that we've only been able to catalog planets, around 13 of them. And for the continuing on with the Babylonian facts, which we'll talk about here in a second, it is actually potentially rooted in the origin of the Epic of Gilgamesh, who was in which he. Oh, sorry. No, I'm misreading that. I'm misreading my own slides. Continuing on. I'll talk about that more in a second, so I can get ahead of myself. So this is a rough picture. Well, here is a star chart of the constellation showing both the I don't see where M83 there's M83, three of the Messier objects. So we have M83 down here that's almost on the border with Centaurus. We have the globular cluster here, M68. Both of those are near the tail section, closer to Spica and overall the constellation, while the open cluster M48 is over here near the head and much closer to Cancer. Over here, but you can see it does border many other constellations throughout the night sky just because of its long, windy shape. Moving on to mythology. So as I did say, this does come from Babylonian origins to a certain extent, and it actually originates from a text known as the Angam, which is a mythological poem from the Mesopotamian region that was shared amongst not just the Babylonians, but also the Assyrians and forget the third one's name. It escapes me, but multiple other civilizations that were in that region. The poem itself describes a contest for the hunting god Ninurta, who slayed 11 monsters on an expedition to the mountains. Sumerian was the third one. I'm getting ahead of myself. So, of the targets that Ninurta slayed, they included a 6-headed ram, a demonic bipedal bison, which, if for those who are not of the Minotaur, may recognize some overlap there of it potentially being an earlier reference to that particular setting in Greece, in Crete, and as well as a 7-headed serpent, which again is which in our case we'll believe to be the precursor origin of the Hydra. Jumping over to the Greeks, Hydra was first described or written down, at least in the earliest mentions that we can find, in a text known as Theogony, the Theogony, which is essentially the genealogy and birth story of the gods in the Greek pantheon that dates to around the 8th century. Despite this being the earliest record we have at it, it also has many of the similarities, many of the basic portions of the myth that we come to associate with the Hydra. Uh, but it does detail that it was the Hydra itself was the offspring of the giant serpent Typhon. That's Typhon, not typhoon, and a half woman, half snake named Ichenda. Also of curious note, which is something I didn't know it going into this, is that the Lunarian Hydra was also apparently female, as the name itself, the way it's written in Greek, is written using a feminine pattern rather than a masculine pattern. But Ptolemy himself, when he cataloged the constellation, used the masculine name in Greek. So a bit of interesting nuance in that. Depending on who you want to get, what sources you look at after the theogony, some of them claim that the Hydra was raised by Hera after its birth as part of her eventual revenge scheme slash beef with Hercules or Heracles, which is the correct Greek pronunciation. The number of heads, though, of the Hydra does grow and change over time, depending on where you look. Sometimes going from 6 heads up to 50, some saying uncountable number of heads. So no real fixed number here that we can definitively say, yes, this is the definitive definition of the Hydra. And the creature was also known to, or stated to possess both poisonous blood and a poisonous breath. Within the Greek mythology, that has two main encounters. One, the first, and probably more well known, is was faced by Heracles as his second labor, where he first set out to slay the Hydra, and in his first encounter with the beast, he attempted to force it out of its hiding cave by firing some arrows into it and confronting it head on, only to be greeted with the fact that its heads regenerate and he was forced to retreat simply because he couldn't kill the beast effectively. And so he retreated and then goes and summons his nephew slash squire slash charioteer Aeolus. And the duo then proceeded to tag team the Hydra, with Heracles coming along and cutting off one of the heads, and Aeolus coming behind and cauterizing the wound to prevent the head from growing. And another potential retelling of the story, Aeolus wasn't there at all, and Heracles used the very blood from the Hydra itself in order to seal the stumps of its head, allowing him to eventually whittle the beast down to this final immortal head, which he cuts off and then goes and buries in another cave in a very distant place, leaving the beast to squeal and swirl in its immortality, with the sword delivering the final blow having been given to Heracles by Athena. Heracles then takes the blood and uses it to coat several of his arrows, which he uses throughout the remainder of his labors. Eventually, though, the poison itself backfires during Heracles' labor to kill the centaur Nessus, in which the poison tainted the centaur's corpse, and one of the items that Heracles had forged from it ended up indirectly poisoning him and killing him. The second of two places that the Hydra appears is in a myth in which Apollo, for some reason, decides to tell a crow that he wants it to go search for water and hands it a cup. The bird itself decides that I don't want to do this, and he spies a nice shiny fig tree, and he goes over and he just takes a break from this quest that Apollo had given him and snacks on the fig tree for a while before returning to Apollo empty-handed, with the exception of a single snake that he captured in its claws, partly as a way trying to lie his way out of the fact that he was a lazy crow and didn't do what he was told, and tried to say, well, I tried to search for water, But this snake here stopped me, so I ended up killing it. Not Hydra. Apollo himself gets really mad at the crow, and his fury, he throws both the crow, the snake, and the cup up into the heavens and curses the bird to forever be thirsty, unable to reach the water-filled cup that's riding along the back of the snake, which serves as an origin of two other constellations, namely Corvus the Crow and Crater, which, since I didn't put this in another slide farther up, are located here along the back of Hydra. We have Corvus here closer to the back, which is a much easier constellation to see because it does have some brighter stars. And then we have Crater the Cup over here just off to the west. So this is the western portion. This is the eastern portion. Just to call that out. Skipping back ahead. So that's it for some of the interesting lore of this constellation. There's undoubtedly more from other cultures, although mostly the Roman cultures would be largely the same since they stole a bunch of the Greeks who stole a bunch from the Babylonians. There's quite a few objects as in this constellation. Most of them galaxies, as we can see here, that stretch all the way into the magnitude 12 range. Most of these, as I did mention, are underneath 10 arc minutes, so would be challenging to see. But there are a slew of bright stars, given its vast dimensions that are well above the magnitude 5 range. And then we have the three Messier objects here at the top of the list. So of the bright stars, we start off with Alpha Hydrae, which is Arabic for the phrase the individual, because there is no other really bright stars in the nearby region of this. So it's, the individual is in solitary. Despite this, the Alphard is also in the position of the heart, roughly, of the Hydra, depending on where you want to believe. And this star falls in the spectrum of a K3, double three, giant, which means it is a very late evolution star. It is relatively bright for stars. It sits at around a visual magnitude of 2, with various stats of being a giant. It is definitely larger than Sol, coming in at about 3.5 times, 3.2 times this massive Sol, around 68 times its radius, and around 1,000 times brighter than Sol itself, at a very close, relatively nearby distance of 117 light years. Interestingly enough, this constellation also, not constellation, the star also appears on the flag of Brazil, representing the province of Mato Grosso do Sul. The flag itself also contains 27 other stars that correspond to the sky above the city of Rio de Janeiro at 8:30 a.m. on November 15th, 1889, which is the Brazilian Republic's Independence Day, essentially. This is a rough breakdown of the stars that do appear on the flag. It is actually, according to Wikipedia, one of the most complicated flags to make because of the positioning of the stars itself. We can see here the box here for number 5 is the representation for Hydra, which is this brighter, larger one here, and then another star here within the constellation Hydra itself. But we also have other representatives here, like Spica over off in Virgo. And we have Procyon and Canis Major from the winter sky, and then some others from other southern constellations. This is showing on the left, we have a star chart showing the position of Alphard within the constellation. And on the right is our Hertzsprung-Russell diagram showing where the star fits over in the evolutionary string of trees. So being with its designation of a K3, it is closer to the top right corner of the Russell diagram. But it's always nice to just see where all this fits, where stars fit in relation to each other. Next up on the list of notable stars, we have R Hydrae, and specifically R and not the Greek letter rho. It is a M6 giant, and it is also a Mira variable star. It is one of oh no, I'm getting myself. That's a different one. It has an extremely broad range of brightness for variables for a Mira variable with an apparent visual magnitude jumping anywhere from the maximum brightness of 3.8 down to a minimum brightness of almost 11. So bouncing in and out between a star that is easily visible with the naked eye versus a star that's not at all visible with the naked eye. With its period shift currently sitting at around 389 days. But as I note down at the bottom, and originally when it was first cataloged by Giacomo Maraldi, excuse me, that he cataloged it over the period of 11 years as having a period of 495 days before that period eventually decreased sometime between the 1770s and the 1950s down to where it currently is today. The star itself has a mass of around 4.5 sols. And because it is a Mira variable star, it does undergo a bit of shrinking and expansion, but consider its average radius is about being about 4 sols, 4.5 times that of the sun, with a luminosity of over 10,000 times the brightness of our own sun at its maximum. Relatively not nearly as close, but still reasonably part of our stellar neighborhood, coming in at 411 light years away. Interesting, the star being part of being a Mira variable, and it is ejecting material into space, which is actually produced what we can detect with telescopes as a visible bow shock coming off of the scope as this material leaves the star and interacts with the rest of the interstellar medium, which we can see here on the right in this raw infrared data from the Spitzer Space Telescope. Well, processed, not raw. And over right showing an artist's rough concept of how the bow shock front interacts with the rest of the solar medium. After R Hydrae, we have V Hydrae, which is a carbon star, which are always fun to go look at because they're always just so nice and deep red. You can find them. This is similar to Alphard in terms of its spectrum, although it is a little bit brighter, warmer, excuse me, coming in as a K03 giant. Despite that, it is a little bit fainter. You will need optics to see it. Reasonably, though, with a pair of binoculars, should be more than adequate, depending on where it is in its variable star curve. All carbon stars are themselves variable stars, so their brightness will change over time. But I did not record what the period is here. I apologize. I missed that. This star does have a visible binary companion, K0 of the K0 class. That is about 46 arc seconds distant, and a potentially a third unseen companion, which we haven't been able to formally catalog. I think we just detected it from gravitational interactions of the star. The star is a little bit much further away. It is actually one of the more distant stars that we would likely go look at, while still being somewhat bright, exceeding the distance of the star Deneb, which is, I think, one of the most distant stars you can see with the naked eye, with V Hydrae coming in at 1,400 light years away. And then, lastly, we have 21 Hydrae. This makes the list because this is a triple star system that does have a faint orange hue to it, if you can find it in very good skies, which will typically be in Bortle 2 or Bortle 3. It is also a K03 giant as the primary element, but with a F4 and a K2 dwarf companions. The primary component itself comes in around 5 a visual magnitude of close to 5, so it is visible as with the unaided eye, as I did say. It does have a mass of about two times that of the sun, with a radius close to 11 sols, and be at around 220 light years away. Always fun to go look at systems that have multiple stars in them. And this is another star chart, this time showing where 27 Hydra is. It is actually very close to Alphard itself. So if you can find Alphard, which is the brightest star over in Hydra, you would easily be able to see, probably with a pair of binoculars, in the same field of view, both 27 Hydra and Alpha Hydra and Alphard together. And the star is on the warmer spectrum. It is closer to the yellowish orange color for the star, despite it being have a distinct orange hue. The orange itself that we see is a combination of all three star components contributing, versus this is, I believe, just documenting what the brightest companion of the group is. And next, for those that do like that are not too big into observing or interacting with or working with individual stars through the night sky, we have talk about the three Messier objects that are available in this constellation, and as well as one other brighter galaxy that might still be a reasonable target to go look at with modest equipment. Starting with the galaxy that was not a Messier object at all. This one is NGC 3621. This is a rough, kind of a tilted, but not necessarily edge-on spiral galaxy that lacks a central bulge. But it does have some well-defined arms to it. It is approximately 21.7 million light years away and has a apparent magnitude of about 9.5, and a size of about 11 arc minutes by 5 arc minutes. So you will need, I would, so to be able to see it, this effectively see this, you would need something like a 6 to 8 inch optic and a decently high powered eyepiece, which I'll show here in a second. This galaxy was first cataloged by William Herschel in 1790, who was, and recently in the news that we may or may not have seen, this galaxy was the host for a Type 2 supernova known as SN 2024 GGI, which was detected on April 11th, 2024. So very recent, almost around the same time as the other supernova that was in Messier 101, which I believe drew a lot of attention to that year as well, around the same time frame. The galaxy itself is host to a supermassive black hole that has a mass of about 3 million sols. This is a rough depiction about how big the galaxy would be in a 2,000 millimeter focal length telescope with a 10 millimeter eyepiece. So this is roughly equivalent to that of an 8-inch Cassegrain and a 10 millimeter eyepiece, which is a very common scope for many amateurs. I know quite a few people that do have this particular setup. So we do see that it does have a really bright core, but it is also a very small object overall, with barely filling up this 10 millimeter eyepiece, which does only have a 52-degree apparent field of view. So it is somewhat small. This is a rough picture. Well, not a rough picture. This is a picture taken off of Astrobin by credit to Daniel Petzen, which he used a 9.25-inch SCT to go take. So we can see a little bit of structure in here, with a little bit of the arms. Moving on, we go into the globular cluster Messier 68, which is in our own galaxy at a partially distance of about 33,000 light years away. This is at least a binocular object, clocking in an apparent magnitude 7.8. Although you could potentially see this with, but it does come out a little bit more spectacularly with higher power optics that you get with a telescope. This globular cluster, like many of them, has a mass of roughly 220,000 solar mass range, with an apparent size of about 11 arc minutes, and the diameter of the whole of the globular cluster clocking it at 106 light years. So, it always is not interesting to see just how dense globular cluster is going to be packing in so much mass in such a small volume. This globular cluster was discovered by Charles Messier in 1780. I'm now questioning that date because I think Messier was cataloging big things at that point, but maybe a typo on my part. Interesting notes about the subject include that it was possibly acquired in the Milky Way during a galaxy merger as the Milky Way absorbed one of its orbiting dwarf companions. We believe this is because the cluster itself is an orbit that is highly eccentric within the galaxy as a whole, with the farthest distance with this globular cluster reaching a distance of about 100,000 light years away from galactic center at the farthest point in the cluster's orbit around the Milky Way. Again, showing what this globular cluster would look like underneath visual optics. This is, again, an 8-inch cement Cassegrain with a 10 millimeter eyepiece. We can get quite a bit of which is a really good size to bring out the entirety of the core, although you could potentially step this down to even a 15 millimeter eyepiece, depending on how big your eyepiece's apparent field of view is. And this is a picture that I took some years ago now, using an 8-inch cement Cassegrain with a focal reducer. I certainly probably try to revisit this one in the future, but it is a very dense core of itself. So very, very easy to stand out against the rest of the background when you are searching for it. And then the next, which is personally one of my favorite galaxies to go look at, both visually and photographically, was Messier 83, known as the Southern Pinwheel Galaxy. This is what's termed a grand design spiral galaxy, of the class SAB, S for spiral and AB for an intermediate, where it has a very solid structure. This galaxy itself is 14.7 million light years away. It is one of the closer galaxies to us that we can see in the night sky. It's also somewhat larger, coming in at 13 arc minutes by 11 arc minutes in size. And the galaxy itself having a diameter of about 120,000 light years, and just barely shy of being in the visible range, coming in at a apparent magnitude 7.8. Although don't let that fool you. That apparent magnitude is roughly just the brightness of the core region itself. The outer spiral areas, from experience, I could say, are much fainter. The galaxy itself was discovered by Louis de Lacaille during one of his many expeditions at the Cape of Good Hope. And it does have significant amounts of active star formation that are visible today in the spiral arms. This is a view of that galaxy. This is, again, with an 8-inch Cassegrain, but this time with a 25 millimeter eyepiece, which allows you to take a step back and get a good view of the whole galaxy itself. And this is an image I took more recently, showing, you can see throughout it the individual red spots of star formation in the three main spiral, well, two. You have this arm here, and then the second arm here of the galaxy itself, with lots of thick dust and red star formation and blue hot young stars that are visible within the galaxy photographically. And that's it for the Constellation Hydra. Any questions or comments before I move on? Give it a second in case somebody is typing something. Doesn't look like that. Any questions or comments? So moving right along, to the main topic tonight. And yes, you will get to hear me talk for another 35 minutes. So this one, we talk a lot in some of these presentations about how big something is or how bright something is or energetic. And inevitably when we put together these presentations, there's you know sometimes you'll come across really big figures of unit numbers or systems of measure that you're like, what is an ERD, for example? Um, I thought about trying to see what I can do to help answer these questions. This in no particular order for this overview, but I will be covering units that are used both, we ourselves might be more familiar with just to sort of set the stage here. But then I will jump around to units that cover a variety of things from units used in radio astronomy, X-ray and gamma ray astronomy, cosmology, and astrophysics. So I'm going to be trying to cover the gamut here. Oh, and orbital mechanics, which I forgot to add here because I added that really late yesterday. Starting off with some of the things that we're pretty sure we should all know at this point, but just for a sake of review, we have the typical degree, arc minute, and arc second units of measure, which are both used to help find things in the sky, but also describe to a person just how big that object would be from our point of view, rather than saying, oh, this object is 100,000 light years away. We might say, oh, this object is 10 arc minutes, which helps us as amateurs quantify, like, hey, is this something I could reasonably see with my gear? Because you recognize that after a certain point, objects underneath a certain range, you might need different equipment to go look at. After that, we can jump over to the astronomical unit, which is one of several units of distance available that I'll talk about. This one is generally used for measuring distances that are within a solar system or such as Sol, or within a planetary system itself, such as the describing the distance between two individual planets, rather than how far something is from the host star. This unit is most commonly abbreviated as AU for astronomical unit, and it is specifically defined as the average distance of the Earth to the Sun, which is roughly 150 million kilometers. So, after the astronomical unit, we move on to light year, which I'm pretty sure everyone's heard or knows at least something about. This is most commonly used for public outreach, occasionally in scientific research. I'll get to why it's not used really as often there. For describing both interstellar and intergalactic distances, it is defined as the amount of distance that a particle of light travels in a vacuum in one Earth year, which works out to be slightly less than 9.5 trillion kilometers. You will also sometimes see this abbreviated down into other units, such as light day or light minute, which will often come across in our own solar system. For example, when dealing with communication lag from Earth to various satellites throughout the solar system. Like, for example, we will say that the communication delay between Earth and the Perseverance rover is upwards of 14 light minutes, versus, the communication delay between Earth and one of the Voyager probes is now somewhere approaching a range of 28 hours one way, 28 light hours one way. The last unit of distance that we'll talk about, I think, unless I'm misremembering, I'm talking about others here, is one known as the parsec. And this is not the Star Wars definition of the unit. This is specifically defined as the parallax second, which astronomers like to use over the light year for many of their papers, simply because there are certain math equations where it's just easier to deal with it, because parsecs is expressed as the amount of angle versus a physical. And so they just stop short of the conversion of not converting angle into light years. Less math for them. That is a typo. This is derived from principles of trigonometry. Typo there. And it is defined as the distance at which one astronomical unit subtends an angle of 1 arcsecond, which is a fancy way of saying that if you sit on the Earth and look at it to the point in the sky, and then you wait 6 months and look at it again, and if that the amount of angle where something shifts 1 arcsecond is defined as 1 parsec, which from a exact standpoint works out to be roughly 3.26 light years. I am annoyedly disappointed that it's not 3.14 light years because pi references, but I think that's probably for the better because then there might be a lot of astronomy students that would not stop giggling at that, which works out as well to about 206,000 astronomical units. Moving on to that, we have several units that are what are known as sun normalized units. These are units that are written in terms of, using the sun as the reference point for them. The first one, which you saw a lot of in the prior presentation, is the solar mass, which I abbreviated as SOLS, SOLs. It is used to simplify the expression of star masses, because when someone writes this star is 30 solar masses, they don't want to sit down and write this star is 60,000 times 6 times 10 to the 30th kilograms every single time in their research paper. So they just abbreviate it as 30 sols or 30 m with this funky little circle that you see here in the line below. Again, astronomers really get tired at writing down exponentials, especially because everything in astronomy is with such absurdly huge quantities. So this is roughly as I said, this is roughly the mass of our sun in terms of a unit. But there are other variations of this as well. We do have mass relative units, such as this that relate to the Earth or relate to Jupiter, which are used particularly in the research and documentation for exoplanets. But you will often see you will almost always see the solar mass crop up when we're talking about galaxies or stars, or in some cases nebula, depending on if that nebula is a star forming region, just to quantify how much material is within that nebula. After that, we have the solar radius, which we use which you did see appearing quite a few in some of the star presentations, which is just used to express how voluminous a star is. It is abbreviated with the symbol R with this little funky circle in it. And one solar radii is just shy of 700,000 kilometers. Remember, this is radius, not diameter. So the sun is about 1.4 billion kilometers in diameter. We have solar luminosity, which is to be a little bit nuanced here between solar luminosity and solar irradiance. The solar luminosity is the total electromagnetic energy emitted by the surface of the sun every single second. It is communicated often as joules per second or ergs per second. We'll talk more about ergs later here in the presentation. It is a very funky unit to try to quantify, and it is abbreviated with an L along with the same funky circle as a subscript that we saw on the other 3 units. And then solar irradiance, which is slightly different from solar luminosity. This is quantifying the amount of electromagnetic energy received by the Earth from the sun. So again, this is the again, as a subnormal term. So this is the energy received from the Earth by the sun every second, which is different by energy emitted by the sun. This is primarily used in the study of exoplanets and particularly inhabitable worlds, which is more of interest into finding out would this planet potentially have water? Does it have an excessively hot atmosphere or those sorts of things? Quantifying how an exoplanet star may be impacting a particular exoplanet's atmosphere. This is defined though as watts per square meter, which is different than joules per second for the luminosity. I did find that there are several different symbols that can be used for this unit. They mostly vary depending on which particular field is writing in that particular paper. Interesting though, as you know, some you may have said, hey, we have this unit, it's normalized to the sun. The sun itself is not a static object, it is dynamic, and it does have the potential, and we also have potential to refine measurements and of the sun over time as better equipment comes online, as we've seen with refinement over the centuries of the sun's diameter itself. And so to help avoid this from being lost on future generations, should those measurements ever change, and to avoid ambiguity, in 2015, the International Astronomical Union said, we're going to make these all have a very fixed and specific value. And if you want to read about what those exact values were, you can go actually read this paper, which is freely available on archive.org. I'd recommend just from screenshotting this number here, which will help get you to the PDF. If you're someone that cares to see what exactly all those units are, because there's more here than I've talked about. Moving on. We get to ergs, which is one of the units that I personally still struggle with because it's just annoying and a lack of context. And I don't know how astronomers deal with this unit. This unit is extremely common in papers when you're talking about energy output of stars or other astronomical phenomena, such as quasars, fast radio bursts, gamma ray bursts, kilonovas, supernovas. It's all over the place. And it predates the standard, the SI units. It is part of an entirely system unit of measure that uses grams, centimeters, and one other unit as the base rather than the kilogram and the meter and then the second. But it's mostly primarily been kept around just because some things are easier to work with because of the subunits that an erg is broken into, and it makes a lot of unit conversions for astronomers a little bit simpler than dealing with the joule for some reason. That's another typo. As I did mention, it is used to report things such as luminosity, radiant flow, radiant flux, but also used to quantify energy received when by spectrographs and in analysis of spectroscopy images. But as I did say, it is used all over the place. I'm just highlighting some things here. Specifically, this unit is defined as, and this is the annoying part, the amount of work required to accelerate 1 gram to a velocity of 1 centimeter per second and have that force exerted over a distance of 1 centimeter. So it's kind of a combination of force with work. It's an annoying unit to try to think about or quantify. It is used as the symbol erg. So it does share the symbol and the subnote as the same as the unit. Conveniently, though, for those who might care, 1 erg does equate to 10 to the minus 7 joules. So it is a very, very small amount of energy. And I don't know why astronomers use it, because it just adds a lot more to the exponential when doing their math. But to relate just how this unit fits into our frame of reference, the Hiroshima bomb has a total output of about 10 to the 20 ergs. Common solar flares that we see in our own system range anywhere from 10 to the 27 to 10 to the 32 ergs released per flare. The sun itself has a luminosity of 10 to the 31 ergs per second. And yes, I'm aware that there is that the luminosity of the sun is eclipsed by common solar flares, which does actually happen. There are solar flares that do outshine the sun. Apparently, I was kind of confused when I did write this slide together. Quasars, which are some of the brighter objects in the universe, have output 10 to the 45, 10 to the 47 ergs, and a type 1A supernova is coming in at the top portion of the range with outputting 10 to the 50 to 10 to the 51 ergs of energy. So just to sort of ground ourselves there. Moving on to other unit, our next unit of energy. For those who also like staring at particle physics papers, especially when you're discovering things like studying of subatomic particles, like the discovery of the Higgs boson or antimatter, for those that like that sort of thing. This is the primary unit of both mass and energy in subatomic research, which for astronomy comes into play when we want to deal with studying cosmic rays, X-ray astronomy, and it crops up occasionally in supernova research and the study of black hole jets and cosmic rays. This is almost this is abbreviated with the unit lowercase e, capital V, and you could convert it roughly to 10 to 1.6 times 10 to the minus 9 joules. So 1 electron volt is almost 100 times less than 1 erg in terms of energy. But again, this is both a unit of mass and energy, because for those who remember our good friend Albert Einstein, where energy and mass are equivalent to each other, it's the same thing here with particle physics. So the electron volt is both a unit of mass and a unit of energy. To give a little bit more context here on where you would see this and what sort of everyday values you might expect, the cosmic microwave background has a standard background rate of about 0.2 electron volts per centimeter cubed in terms of overall energy. A visible light photon carries roughly 1 to 3 electron volts. A cosmic ray can carry upwards of 10 to the 18th power electron volts, which is there might be a mistypo there for me on gamma ray bursts. But a gamma ray burst can carry anywhere from 3 to 30 giga electron volts, which would be 10 to the 9th. So a gamma ray burst particle, when we see them from Earth, carries not half the total energy, but 9 orders of magnitude less energy than a single high energy cosmic ray. I should have been a little bit more consistent there in using power notation rather than SI prefixes. My bad. We then have the Jansky, which is a unit of energy most commonly used in radio astronomy. It does appear occasionally in those who study gravitational waves. It is 10 to the 26 watts per square meter per. So there is a relationship between the energy received over a particular wavelength range. In most contexts, though, this is roughly reported as the energy received by a radio antenna over a fixed radio spectrum range. And sometimes they will omit the frequency altogether for specific instruments. Other times they will, if it's depending on where the detection was, if it was an abnormal frequency for them, they will explicitly report the frequency. So they might say something like this irradiated 1.4 millijanskis over the 1.4 gigahertz spectrum. You might see things written out like that. The Jansky itself is often reported as a very small unit for us in radio astronomy, with most modern radio instruments dealing with values of the millijansky range. For example, we recently detected the Very Large Aperture Array in Chile measured the energy released by a black hole tidal disruption event as receiving 1.4 millijansky in the 5 gigahertz range, so very small units overall. And I didn't give any other examples. It's one of those units that's still kind of hard to quantify and provide a good everyday reference for just how big of a number is. I struggled with finding more examples of that I could relate to. Moving on, we have the redshift and blue shift measure, which for those who, this is directly coming from the Doppler effect. And specifically, this is the shift in wavelength of a known signal. another typo there, which is typically observed as the source emitting the signal moves closer or farther away from an observer in a fixed position. We often It is mostly used in astronomical research as an analog for how distant an astronomical object is. So rather than reporting, hey, this object is, 1.8 billion light years away, they might report a specific Z value instead, which uh, is a little bit more precise for them to quantify because sometimes you don't want to work back and report light years for just depending on the instruments that you're working with. This is favored specifically in studies of the early universe in cosmology. You may have seen this occasionally crop up in James Webb telescope pictures as they talk about, well, hey, James Webb just observed this most distant galaxy with Z equals 13.6 something, for as an arbitrary example. Uh, and again, this because it's easy because of how it's measured as through spectroscopy, they'll often just report the Z value over the light years and uses the symbol Z. This is a dimensionless unit. That means there's no Z equals like 1.6 photons per second or that sort of thing. It's just Z. There's no other units associated to it like kilograms or meters or that sort of thing. And it's simply computed as just essentially a delta ratio where you look at what wavelength you observed versus what wavelength you think was emitted over what you think it was emitted. And that gives you a nice handy dandy ratio. I'll show another an example of what I mean by that here on a slide after this. So this is kind of more detailing here what you would expect with Doppler shift. So you notice here that this is a reference spectrograph of the sun, and then on the right we have the absorption lines of another distant galaxy that has, well, that's incomplete. I apologize. That has been far enough away that the spectrum itself has shifted. And so what astronomers are doing is like, hey, we know where hydrogen is. And so we can look at the spectrograph and see like, hey, how much was, hydrogen shifted? Because we would expect, hydrogen dominating a lot of the spectrum that we see. And so we can just see that, hey, this was shifted, by a very small amount. And that is how they work out to find out, this sun is the observed reference in most cases. And then the right is the emitted in that equation that I showed on the previous slide. But Z values themselves are kind of, hard to measure, not hard to measure, but hard to really relate to in terms of where do they fit overall in this distance scale. And as this graph shows, it's not a linear relationship. It's not, it is almost an exponential curve that does taper off after a certain point. So we can see here that, once you get past into the 12 billion light year range, that it sort of tapers off much more slowly as we approach, Z equals 7 to Z equals 13, which is the farthest here. We get much farther. And so things are really more sticking into a very fixed range once we get into the 7 to 13 range versus objects that have a Z index between like 0 and 7 are really somewhat close in the astronomical terms. So really it's sort of a competition amongst astronomers at this point to see who can get the larger number to find the most distant object. Ugh. Moving on to orbital mechanics. We have a couple of things that crop up as we ourselves study comets and asteroids. The main one that we'll often see, which those who have followed anything with the interstellar comet 3I Atlas, you'll see this also came up a couple of times, as well as a couple of other units that we'll talk about here. This is the orbital eccentricity is also like the Z index, a dimensionless unit. It is used, abbreviated, expressed with the symbol E for eccentricity. It is defined as the amount by which an object's orbit deviates from a perfect circle. with values falling from 0 to unbounded. So between 0 and 0 to 1 follow circular and elliptical orbits. All the planets and majority of the asteroids and comets in our system have orbital eccentricities between 0 and 1. Objects that have an orbital eccentricity of 1 or greater than 1, have parabolic and hyperbolic trajectories, which means that these trajectories are escape trajectories. Objects with an eccentricity greater than 1 are not bound to our solar system or to, in the case of, we managed to measure the orbital eccentricity of an object in another solar system, like say an orbiting star, for example. These objects will eventually escape each other's orbits and move over as individual objects. Like in the case of 3I Atlas, it has a orbital eccentricity of 6, which is a very hyperbolic trajectory. Oh, I'm getting ahead of myself here. Okay. Yeah. So the first portion is kind of recapping what I said here. Hyperbolic trajectories have significant energy and they will escape their parent's gravitational well. Whereas parabolic trajectories are kind of like that Goldilocks zone of just right, just the right amount of energy in it that that object will escape. Obviously, this is exactly parabolic trajectories are very rare because it's very rare for an object to have exactly enough energy to escape the solar system. So it'll generally be slightly greater than 1 or less than 1 rather than exactly 1 in measuring. So most objects that we you'll probably see about are either elliptical orbits or hyperbolic orbits. Or in the case of satellites, which may have a perfectly circular orbit because of that's just how we did set them up. Albedo is a measure that commonly appears when studying asteroids, comets, and satellites. This is a measure of essentially how reflective a surface is of generally visible light, but sometimes also radar wavelengths. It is a value that ranges between 0 and 1. So you could think of it as a percentage, like with 0 being this object absorbs nearly all light. So 0 is essentially a fully black object which would be, as an example, a black hole has an albedo technically of 0 by definition of being a black hole. And 1 being an object that is fully reflective. The object itself will reflect nearly all light that you can see from it. Again, this is kind of a subjective nature because when we think of albedo, when we think of reflected light, we ourselves like, hey, I'm shining a light bulb onto this other object. I should expect to see the same amount of light back. It's not quite the case here, which I'll explain here, which will explain some of the figures you see at the bottom. And as I did mention, this is sometimes expressed both in radar and optical light. So radar objects will have much smaller albedos, which is what we commonly use for satellite tracking, but also a lot of asteroids are cataloged nowadays with radar as well in order to get better handles on their characteristics. An example albedo values just to sort of ground things, which I was also surprised about on some of these, is Enceladus is actually the most reflective object in the solar system. It has an albedo of almost 1, which at a certain degree does make sense because Enceladus is an ice moon, so we would expect it to reflect nearly all of the light that it gets back because it is a mostly white object. But surprisingly, the asteroid Eris in the asteroid belt has a very high reflect albedo too of about 0.96. Whereas the moon, Luna, has an albedo of about 0.14. So despite being an object that is very bright in our sky, the moon itself absorbs a significant amount of the light that hits it, that it receives from the sun in the visible wavelength range. And whereas the average comet nucleus will typically have an albedo of about 0.04. So most comet nucleus themselves, despite having very bright tails, the nucleus itself is basically a dirt dust ball, so they don't reflect a lot of individual light. Again, albedo itself is not uh, tied specifically to the object size here. This is purely how much light is emitted by an object if you know how much light it received at its distance. So the size has nothing to do with the albedo. And this is the last unit of measure, which is what you'll actually see in the, if you regularly peruse Wikipedia trying to understand star statistics or learn about stars, you might want to go look at, but also in star catalogs, like for those who might use digital star catalogs like Telescopius or Stellarium. This is a system, the UBV is a system used to help describe the color of a star, which is a more rather being as part of the OBAFGKM system, which we describe as like, this is a G class star. This is a specific way. This is a system that is measurable, which is whereas the other system is somewhat of a subjective system. So it is taken exactly through sensor measures. To derive this, the star itself is measured through three independent filters: an ultraviolet filter, a blue filter, and a visual filter. And these filters are very specific because when the system was first created, they were geared towards film. And obviously, with the evolution of CCDs, we have had to evolve this system, but I wanted to keep it still in line with prior measurements. So through a lot of calibration efforts, that these units align and make sense. Once you have those three individual filters, we're again recording the magnitude of the received light over in specific filter wavelengths, and then you'll report the UB color, which is the difference between the ultraviolet filters and the blue filters. So a high UB magnitude means that the star would be very bluish or nearly whitish. And the BV color index is kind of the opposite, which is getting in more in the blue and visible solar range, like with the sun. So both of these together are used to quantify the star's temperature. The star's color, and we can also use this indirectly to compute a star's surface temperature as well. And that's it for a lot of the units that I had. Any questions? Anything we want to pick apart here? Anything that didn't make sense? There's a lot of units.
Yeah, very clever idea to talk about the units, Connor. Very useful information. Could you maybe go back to the page on luminosity? I kind of didn't really absorb a couple of things I wanted to ask you about.
There we go. There we go.
Yeah. Okay. So the first question is in terms of luminosity. I guess I had never really thought about it, but your first small bullet there, the total electromagnetic energy emitted by the sun, or I presume any star, and I presume that's probably flux. That's probably per square area, or not necessarily square, but some per area per second or something like that. But what caught me off guard there was a total electromagnetic energy. So that's opposed to just the visible spectrum. Then I presume you're saying here.
It's
So
across infrared, ultraviolet, all of it.
well,
Again,
including
again, this is specific
X-rays and
to the solar luminosity here. So this is not general luminosity, which may have a slightly different definition. And the way it is expressed in astronomy is often as the solar luminosity, which is the amount of energy emitted by the sun as the unit of the unit one value.
Right.
Now, the reason it's total electromagnetic energy is because not all stars radiate along the same wavelength, which is why it's, you'll have like O class stars, which are very bright and ultraviolet, but not nearly very bright in, say, the reds and blue range, the reds and green range, you know.
Right, what I'm trying to understand is you say the totally electromagnetic energy. So would that include microwaves and uh, X-rays and basically everything, or are we really kind of focused in the near visible range? Because I mean I'm imagining that when you look at any star, you probably see some have a lot of uh, energy at different wavelengths, not necessarily just the visible wavelength.
This is full spectrum, because to your point,
So it is full. Okay.
stars don't radiate over only the visible spectrum, and we have
Right.
instruments that specifically don't measure visual spectrum, like James Webb is pure infrared.
Right.
So
So, so,
having it
so
confined to visual spectrum is not a helpful unit.
yeah. So, so
It's
so again, like
full
on the
resolution.
Hertzsprung-Russell diagram, it would be again the entire radiation spectrum, not just the visible. So that's kind of a little different picture I had in my mind from when I first learned about Hertzsprung-Russell back in
This does
1960 or something.
don't try to equate luminosity to where it fits in the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram, while it is primarily a way to communicate color, not necessarily brightness.
Okay, well, that's kind of more the way I had thought about it. Okay.
I may get yelled at this later. Let me go pull up. No, no. Uh, so you will see things like the solar luminosity here, as we can see it like in 10,000 on a logarithmic scale. But I don't really find it helpful to from our perspective, it's the Hertzsprung-Russell diagram is really beneficial to communicate the relationship between a star's color and its luminosity.
Yeah, so I guess I had always kind of thought of when we say luminosity there, I kind of thought just, brightness. But if luminosity is measuring the entire spectrum, then it would really be the luminosity in this definition would be the entire output of energy, not just again how bright it is. Did you see what I'm
Yeah, so
confused? What I
I
was,
can see your
yeah,
confusion here
yeah,
is like when you say like, oh, we have this O class star that's 1,000
yeah.
sols or 1,000 solar luminosities. That statement itself does hide the fact that that star is not is much more irradiated along certain spectrums than just pure visible.
Hmm.
Which I can see why
Yeah,
where yeah, I get you where your confusion is now. So, yeah.
yeah. It's just I'd never thought of it in that regard before. So kind of a new way of looking at it, if that's
Yeah.
what it were to me. So yeah, thanks.
And with that, then, if I don't have any more questions in the chat, I'm going to go ahead and
Well, I've got two silly ones for you on the erg. Are you familiar with the joke about the definition of the erg?
I am not.
Oh, well, then you need to know this then. So apparently moving that 1 gram for 1 centimeter is a dyne of energy, I guess. And so I guess I've heard the joke a couple of different ways, but um, what you do is you take um, a centimeter and you hit it over the head and you kill it, and a dyne centimeter goes erg.
Yeah, I
I'm
specifically did the
sorry.
long form version of the definition. Rather, did see that dyne cropped up, but I didn't really think people would understand what a dyne is. So I put the long form definition, which is where you get this exerted over. This is a one
Yeah,
second portion.
and I have to tell you, I learned it back. I learned that back in engineering school, and I've never forgotten what an erg is. Uh, okay. Anyway, the other question was, okay, the Star Wars parsec. I heard some people trying to rationalize what that meant, and one definition I had heard was that it's not so much the angular thing that we know parsec to be, uh, but more a case of the Kessel Run is some sort of a smuggling route, and
Star
that
Wars Star Wars uses it not as a unit of distance, but as a unit of as a rough unit of time is how you could
well,
interpret.
that's what I always thought, but I recently heard someone try to justify that it was a unit of distance, and that it was, if I remember what I heard correctly, that it, basically being a smuggler's run, he found and his ship was able to take a shorter path through a field of black holes or something, and so he was able to do it in a less distance. Uh, through this field of black holes or something like that. I'm just wondering if you'd heard anything related
I
to
mean, the
that.
official word for Lucas is just like I liked how it sounded, so I put it in the movie.
Okay, and I'm happy with that.
That's the official verbatim. I think I heard at one point from where people were when Lucas said, "What is
Yeah,
a parsec?" It's like I don't know. It just sounded cool, so I put it in. Didn't
I
care what it
I
actually
like
meant.
that.
I just put it in because it sounded cool.
Yep.
Okay, so, so let's stop the
Okay.
recording here.